थर्ड को दोपहर तक ऐसा लगा कि सेंटर में आपको कुछ भी ना हो तो भी
यार जिम इस पेज को स्पॉन्सर करें थोड़ा सा, तो इस पे लाइक ज़्यादा हो जाएंगे। अभी किसी को नहीं पता।
आप इसको ना शेयर करें ना अपने पास।
मैंने काफ़ी दफ़ा किया हुआ है यार, लेकिन स्पॉन्सर करने से ज़्यादा होते हैं वो पैसों पे, इतने लाइक्स इतने पैसों पे होते हैं। मेरे हाल में 150 पे 3000 है।
गाड़ी को पकड़ना है ना तो गिरने नहीं देना कौन सा भी है वो जो कि क्या रहता है Guys, the video people, you guys want to come over? They're ready to try. Ready to go. So I need a camera. So what went wrong? I know, but what went wrong? No. Yes, something wrong with your delta T because I think they hit at the same time. So your range is fine. The time. Time delay. Reaction time. Yes, you guys have, so think about it, there's a word called reaction time in it, right? That needs to make sense. So you can actually calculate that, right? Like you can calculate how much time later should you release the
He's right.
अगर आप हमसे नहीं हुआ तो आपको करना है
Try again. Reaction time, right? Try again. One more time. Lisa, we're done. Okay, what went wrong? Now let's try to figure out what went wrong. Yeah, exactly. You need to find the velocity because that's what you do in your range. You should have told us that ahead of time. We should have done something to our faces. That's so unfair. हाँ,
You still have
ठीक है,
time. You
क्या
still have
है?
time.
अब क्या फायदा? आपको देख लिया सारी
कोई बात नहीं, एंड में करते हैं आगे.
अब कोई फायदा नहीं. This is the sound one. Making ये vibration है ना? ये सिंपल हार्मोन है क्या या ये वाले हैं? इस तरह वाले? कितनी आते हैं हार्मोन? 5? वो जाहिर है हाँ. इसके ऊपर आप वो भी बना सकते हो. यूँ नहीं मिलता है कि नहीं वो कॉर्न स्टार्च और पानी का मिक्सचर कभी किया. वो कॉर्न स्टार्च और पानी का मिक्सचर डालें ना डिफरेंट रेजिडेंसेस पे करें, उसमें भी सिंपल हमारे कार्य शुरू होता है.
मैंने कहा आप दोनों की बनाना.
वो हाँ वो 2D आ जाता है ना. ये 3D में आते हैं वो सारे आपको नजर आते हैं. कॉर्न स्टार्च और पानी का मिक्सचर होता है. मुझे एग्जैक्टली उसका नहीं पता कि वो उसकी क्या होती है. वो काफ़ी थिक सा ग्लूई सा लिक्विड बन जाता है. तो वो हाँ उसमें अगर वो खुला हो जाए तो वो नहीं करता. बहुत ज़्यादा भारी हो जाए तो भी काम नहीं करता. तो वो हम लोग करते होते हैं के बाद उसके ऊपर डाल. वो इतना होता है कि आप उसको आराम से कार के साइड पर रखें. आराम से. हाँ सारा कुछ ऐसे ही है. Now the competition starts. ये इम्पोर्टेंट नहीं है किसी का हुआ है कि नहीं हुआ. ये इम्पोर्टेंट है कि फिगर आउट करें कि क्यों नहीं हुआ. That doesn't matter. टीचर्स आएंगे तो आराम से कर रहे हैं. स्टूडेंट्स इतना शोर मचाना शुरू कर देते हैं. साइंस का आवाज़ ही मुझे खुद आवाज़ आपने कोई फिजिक्स की ऐसी क्लास में देखी होगी जिसमें स्टूडेंट्स कहें कि नहीं हमें अभी और टाइम चाहिए. हमें अभी और टाइम चाहिए. हम अभी तैयार नहीं है करना. we're not ready to leave now. we're not ready to leave. So like नहीं टाइम खत्म हो गया. नहीं we're not ready to leave. I have to kick them out. हाँ सीरियसली. और वो वाले स्टूडेंट्स हमारे वाले तो फिर वो कंपटीशन परवाह नहीं होती, सी आ रहा है तो खैर है, कोई बात नहीं, चलो पास तो हो गया ना। वो क्या हमारा लगा नहीं है, हमारा लगा नहीं है, क्यों नहीं लगा?
प्लम लाइन्स एक्स्ट्रा तो नहीं है, वो एनर्जी कॉन्जर्वेशन पे नहीं है,
कोई एक
वो तो आर की एनर्जी कॉन्जर्वेशन में जो दावा नहीं लग रहा वो निकाल के देते पड़ा जो आगे उसको पनीर के नीचे हम बना पॉइंट करने के लिए
बेशक वो पॉइंट ना भी रफली अगर तार है लंबी और छोटी जानी में
पिन नगर लगा
Alright, we have 5 to 10 more minutes, then we have to move on.
Well, one person be done. We did it.
And it was from YouTube, but
लोग हैं 50 इंच आगे हैं
All right, just 3 or 4 minutes, 3 or 4 minutes, 5 minutes.
सब लोग जाएंगे
No, you are done.
I don't know what you're asking.
No, you're done.
I don't know.
All right, so let's get settled down for the next activity. Thank you very much. Thank you, Dr. Samia. Thanks a lot.
Thank you. Who can I make to drop the cars? Somebody brave enough to try it now? No? That's okay. We tried.
All right.
Thank you guys.
So please settle down. Make yourself comfortable. You should be able to have this blackboard in your view. So make yourself comfortable. Sit down, please. Now what? In the next 1 hour. You see, after lunch, we're going to start experiments. So, to our best of abilities, we have paired our people from different nationalities, different levels of experience. So there's a professor who will be working with a student. So we've done this pairing, but it's not hard and fast. So you can all, it's not recommended, but you can change pairs. There are some pairs in which the second person is missing, so you can just recombine. But this is going to happen after lunch. So what I'm going to do now, in an hour, I'm going to perform a simple experiment in front of you and take you through the complete process of performing an experiment, which includes making a table, which includes quantifying results, quantifying uncertainties. Alright, so it's a 1 hour long demonstration. So what we have in front of us is the compass, and we know there's a magnetic field everywhere. So there's a magnetic field everywhere, and the magnetic field has a horizontal component and a vertical component. Okay, and this changes from place to place. We want to find out this field, and we don't have a magnetometer, we don't have a Gauss meter, we don't have a mobile phone that has a magnetometer, we don't have any other sophisticated device. So we just have a magnet. Right? So this is a cylindrical magnet, and we have quite a few of them. Alright? So could anyone come up with an idea of how we could find out the Earth's magnetic field at this longitude, latitude, Lahore, with the help of these magnets? Could anyone come up with an idea? Just throw some idea. Anything you can think of. You can have slide, you can have something that's available in a first year lab, a string, a stopwatch, perhaps you make a pendulum, something. I give you half a minute to think about this. No electricity. No electricity.
Because you are in Pakistan.
Yes, I have a demonstration for that, but no electricity. Nothing to the AC mains power supply. Okay, I walk in the laboratory for half a minute. Just think about this. Raise your hand and speak up. Floor is open to all. Think like a pendulum. Galileo, think like Galileo. 17th century. Galileo only had a pendulum. He had his pulse, something that's oscillating. Angular deflection. Right, so he's on the right track. Zafar is on the right track. He's thinking about angular deflection. Right, you find out the Earth's magnetic field. Cavendish did this in one of the famous experiments, most sophisticated experiment. He found the Earth's magnetic field by torsion. So can we think about torsion, angular deflection? Good point, Zafar. So now how do we apply torsion to a magnet? Tied to a thread.
Small mirror piece.
Good, so you're on the right track. Good. So you have a string, you can attach magnets to a string, and look at the angular deflection. You attach a mirror, you laser, and then you look at the deflection. That's something slightly more complicated. If you would like to do a sophisticated experiment, that's how you would do it. So angular deflection is also related to oscillation time period. So what we could do in fact is, I give you another hint. We know that a magnet has a moment, nu. And if it's inside a magnetic field, it experiences a torque. It twists inside a magnetic field. So if you have a magnetic field pointing like in this direction, this is my magnetic field, and I have a magnetic moment, right? Which is a magnet is a moment pointing like this. Then a torque is going to act on this moment, and if you look at the direction of the torque, u cross b, torque is an outward, which means that this moment would like to align itself with the field, and it's going to twist. Now when it twists, it goes here, comes here, the This Newton's laws of motion, it accelerates. Torque is rate of change of angular momentum. It comes here, then due to its momentum, it goes to the other side, and then it starts oscillating, just like a pendulum. So if I have a pendulum and it deflects, it then starts to oscillate under the gravitational field. Likewise, if I have a magnetic moment, this is a magnetic moment, I would like to see how it twists inside the Earth's field. And when I know how it twists inside the Earth's field, this process is going to be, I can write Newton's equation for this. So what I would like you to do in the next 2-3 minutes, you see, experiment and theory go hand in hand. You have to think first. Like in the first problem, you actually came up with the equations of motion. So this is the starting point. So now what I would like you to do is just think in the following sense. I have this string here. It's tied from the top. Okay? And there's an Earth's field. So I take two magnets. These are cylindrical magnets. I can attach several magnets together. And what I would like to do, I would like to hold this string in between the two magnets. Okay? And just leave this for a little bit of time so that it all equilibrates. Hands always get dirty in the physics lab, but that's good. We all belong to dust, we know that. Now this magnet, in its resting position, if I move the other magnets away, in its resting position is pointing in a certain direction. What is that direction? It tells you something about geography. What's the direction which is, why are these magnets not pointing like this? Why are they pointing like this? Because north and south. So this is a compass. This is what the Chinese invented 5,000 years before Christ. This is a compass. This pointing in the north-south direction if other sources of field are far away.
North of the Earth magnetic field.
North of the Earth's field, which may be different from the geographic north, slightly different. Okay? So this is its equilibrium position, and it's in the Earth's field dictates what direction it is pointing in. Now, if I want to twist this, as you said, and as you said, or twist this a little bit, it's going to oscillate about its rest position with a certain time period, with a certain friction, or with a certain frequency. And it's eventually coming to rest like any pendulum. Alright, so you can find out the time period. Now, with this equation in your mind and Newtonian mechanics, something that you've seen in the first activity, I would like you to write an equation which relates the angular change, theta, with the magnetic moment and the field. Can you write Newton's laws, Newton's second law that describes this motion? 3 or 4 minutes, try it out. If someone writes it, fine. Otherwise, I'll explain. It's its rotation. Remember, instead of mass, we have moment of inertia. Think about F equals ma. We have to find the rotational version of this. It's twisting. No G. What is G? What is K? Which linear acceleration? Okay. Okay, fine. Now convert this into angular acceleration. Angular. It's an angular motion. Exactly. Now, express alpha in terms of theta. Theta is small. Theta is small. Good. Now, when theta is small, what happens? Sin theta becomes theta. Good. Fine. We have the equation of motion here. It's very good. Anyone seeking help? I can provide help. Good. I think you're on the right track here. The torque, if I write this in a scalar form, the torque is rate of change of angular momentum, which is moment of inertia, d square theta dt square. This equals mu v sine of theta. And if theta is small, this becomes theta. D square dt square is mu v over I theta. This is my equation of motion. Now you can solve this equation of motion, right? It's using the conventional techniques of ordinary differential equations. It turns out that this theta depends upon time. And how does it depend upon time? It's some amplitude theta naught sine of omega t. Now omega is inside this equation. Mass attached to a spring, pendulum, this object, all of them are the same. They're all second order systems. They're all the same. They all have the same model. Okay? So it's not different from a mass attached to a spring or a pendulum. So this object here is, what is this object? Mu b over I. How is this related to time period?
Inverse.
This is frequency. This is the square of the frequency. Alright, we have Hooke's law. D square x over dt square is omega square x. Omega square is k over n. So this is omega squared. Omega is the under root of this. So my equation is mu b over I under root time with some phase perhaps. So this is my equation of motion. Now if I can find out the time period of this oscillation, I can find out the Earth's speed if I knew the moment of each one of them. Alright? Or I can find out the product of the Earth's field and the moment. So this is my equation here. Now with a simple model, we have started talking to an experiment. We can think of how to design an experiment. Simple physics, what we learn in physics 101, first course. We can now start to apply this to a real experiment. So I'm going to erase everything else here. And now what I would like to do, I give you 2 minutes to think about how will you actually perform this experiment. Just 2-3 minutes, think about this. I have several magnets. I have a string. This is my equation, this is my motion, this is my model. How can I find out? Suppose I give you the moment of this magnet. How can I find out the Earth's speed? What kind of experiment will you build? What kind of experiment will you design? What's your scheme? Think about this for the next 2-3 minutes and then we'll talk again. Keep on discussing with your friends. Think about this here. You want to find a proper value of the Earth's field with its uncertainty. What would you do? You have several magnets at your disposal. एक ही दफा बस नहीं stability. How will you change? What is the will be different between experiments? Think on these lines. What do you make several readings? You want a good estimate of V. Statistically small answer. Most welcome to raise your hand and explain it to everyone else. How will you perform this experiment? To find the earth field. I give you the moment. Brilliant calibration. Anyone? Dr. Sabab, thank you. Please. Can you describe? Changing the number of magnets. You have just have these magnets, but you have quite a few number of them. You change the strength, or which means you change the moment, magnetic moment. Right. And what do you measure? Do you need the deflection? No, you don't. Anyone else? Yeah, this is fine. This is on the right track. Anyone else could give a more concise answer? This is fine. Yeah. So what you would do is, anyone? Measure the time period. Exactly, this is how you would do it. Fine. What you have is, you have these two magnets. You nudge them slightly, they will start oscillating. Find the time period. Then you change the number of magnets. When the number of magnets changes, what does change? What changes? So you have the time period is 2 pi over omega is I over mu v. This is your time period. When you change the number of magnets, what's changing here? Time is changing, of course. What else is changing on the right hand side? V is not changing. Mu. That's it. I is also changing. Okay? So you change the number of magnets. You know the moment of inertia of a cylindrical object given in textbooks. So if I have one cylinder, I have one cylinder, radius r, height h. Now this is my axis of rotation, right? This is where the string is. So I need to find the moment of inertia about this axis of rotation. This is my axis. The moment of inertia changes depending upon where the axis is. So my moment of inertia is so this is a formula that's given in textbooks. 1 over 12, the mass of this object m h squared plus half 1 over 4 m r squared. This is the moment of inertia of a single object, and you have two of them. It's rotating about its axis, you see? Right. There are two, so it's rotating about it. This is the axis of rotation. Alright. So you find the moment of inertia Okay? And how does mu change with the number of magnets? How does I change? If I make the number of magnets capital N, this H becomes n times H. This becomes n times H. R remains unchanged. Mass becomes n times the mass of each one of them. So I can find the moment of inertia of n objects. And how does mu change? If I have two objects, two moments, the moment of each one of them is mu. What's the moment of two objects, three objects? If I have n of them, it's n times mu. If all of the magnets have the same magnetization, their moments are going to add up. So I put in all of these values for n moments, n, and then I get a relationship between the time period and the number of magnets. And if I work out the algebra, which you can do on your own, the final result is the following. The time period is 2 pi, the mass of each one of them, the moment of one of them over p, 1 over 12 h squared capital N squared plus 1 over 4 r squared raised to power 1/2. This is my formula. So now what we could do is we could change the number n. This is in our control. We change the number n and then we make a plot between the time period and n squared. If you make a plot between the time period and n squared, we can get a straight line. That straight line can tell us something about the field. So let's perform this experiment. Alright? Now could you, now we have two magnets here. Alright? Okay, so can you start straight away? Can you measure the time period of oscillation of these two magnets? Oh, these ones. So you just nudge them slightly. Listen. That's for tomorrow. Alright. So time period, please. Just slightly nudge it, slightly. Horizontal, in the horizontal plane. Have you noted down this formula? This is a time period for what's how many oscillations did you count? 30 seconds. Alright, so what Hassan, are you Hassan? What Hassan has done, he took two magnets, n equals to the time for 10 oscillations in seconds is, what's the time period for 10 oscillations? 30 seconds. 13 seconds. Just no, nothing beyond this decimal point.
0.03.
Alright, this is important. 13.03. This is what the stopwatch is measuring. Now we have 4 significant figures here. This 0.03 is being returned by the instrument. So we would like to note this down. Alright. Now our best estimate for the time period. We must have a best estimate for the time period. Is just 10, this divided by 10. Now this looks simple stuff, but I'm going to go through this slowly so that you get a feel of what's going on here. So the time period is 1.303 seconds for n equals 2. Alright. Now the question is, you could do more experiments, we don't have time, you could do it once again and take averages, etc. But we don't have time for that. But what's the uncertainty in this value? You see, what is this 3? Do you believe this 3?
No.
It's your psychology. Your psychology says no, but scientifically, do you believe the 0?
Yes.
Why? Why do you believe the 0 and not this 3? It's your hunch feeling. Is it your psychology? What do you have to come up with scientific answers? Do you believe this 3? It's probably that this 3 is problematic. It's probable that this 0 is problematic. So there's a probability that you have confidence in each digit. So any digit that you write, for a theorist, it doesn't matter. 1 is the same as 1.0, as 1.00. A theorist doesn't care. But for an experimenter, if you write 1.0, it's different from 1. And it's different from 1.00. Each digit that you write has a meaning, has a significance. So now we would like to find out the uncertainty in this. What's your plus minus? What's your uncertainty? Generally it's called error. I don't like the word error. It's not an error. Errors are human mistakes. This is an uncertainty. It's a part of the process. So what's the uncertainty in this? There must be some uncertainty here which leaks into this value. There's some uncertainty here which just trickles down here. So what's the uncertainty here? What is your uncertainty in the measurement of with the stopwatch? 0.01? Your least count? So one thing is the least count, what you call the least count. So you say it's 0.01 or some fraction of 0.01. It's more sophisticated than that, but okay, let's say 0.01. But is that the biggest? This is 10 milliseconds. Is that the biggest uncertainty here? Is there anything bigger than this or smaller than this? Is that the only source of uncertainty? Look at your first experiment. What do you mean human error? Reaction time. The response time was actually far, it outweighed this small uncertainty. So the human response time, it's not an error, it's our inability as human beings. So we don't say error. Errors can be rectified, this can't be rectified. So there's some response uncertainty. And there are lots of experiments, studies that tell us what the uncertainty is. Generally, it could be 200 milliseconds if you're really good at start and stop. Okay? So, if you really practice well.
I think it's for average human, it's about 3/4 second, 0.7.
0.7?
Yeah. For average.
Okay, let's keep it round figure 0.5. 0.5 seconds is the response uncertainty. So what's the response uncertainty in here? 0.5 times 2 because you start and stop. So it's 0.1 second. And this is much larger than the uncertainty associated with this least significant digit. So the uncertainty in your measurement of 10 oscillations, uncertainty here is 1 second. 1. 0.5 into 2. Start and stop. It's 1. And when you write uncertainties, you only write generally one significant figure. You don't write 1.0. Okay? Generally in uncertainty, only one significant figure is enough, or at the most two. Now this is the uncertainty in this value. What's the uncertainty in this value? You divide this by 10. Alright? So the uncertainty in your time period in seconds is this thing divided by 10, which is 0.1. So your time period is 1.303 plus minus 0.1. But this means that